To predict the behavior of a gas using classical mechanics, you would need to calculate the exact trajectory and momentum of roughly 10 to the 23rd individual atoms. The scale of the data makes individual tracking impossible. Statistical mechanics bypasses this by calculating the probability of observing macroscopic properties like pressure, volume, and temperature, rather than following every particle. The primary tool for these calculations is the statistical ensemble. An ensemble is a collection of mental copies of a system. Every copy is prepared under identical macroscopic conditions, meaning they all share the same physical constraints. While the macro-scale rules are the same, the microscopic arrangement of particles inside each box is unique. By defining the boundaries of these boxes, we generate three probability frameworks: the microcanonical, canonical, and grand canonical ensembles. At macroscopic scales, all three yield the same thermodynamic results. To calculate probabilities, we must first account the total number of possible microscopic configurations, known as microstates. This counting happens in phase space, a mathematical map where every point represents the exact position, Q, and momentum, P, of every particle in the system. Because these variables are continuous, we divide the phase space into discrete cells to make the configurations countable. The fundamental unit used to normalize the volume of these cells is Planck's constant, h. The physical constraints we impose on a system determine how we slice and count this phase space, leading to our first ensemble. The microcanonical ensemble models a completely isolated system. The particle number, n, volume, v, and total energy, E, are strictly fixed. In equilibrium, every accessible microstate satisfying these strict constraints is equally probable. We represent the count of microstates with the function omega. Because energy is fixed, the integral only counts states within a narrow shell between E and E plus delta E. An n factorial term is included in the denominator to account for the fact that particles of the same type are indistinguishable. This microscopic count defines the system's entropy. According to Boltzmann's definition, entropy, S, is the natural log of omega multiplied by the constant Kb. While theoretically sound, strict energy isolation is difficult to achieve in experiments. Most physical systems fluctuate in energy as they exchange heat with their surroundings. In the canonical ensemble, the system contacts a heat reservoir. It is no longer isolated and can exchange energy with its environment. Particle number and volume remain fixed, but temperature, T, is determined by the reservoir. This causes the system's internal energy to fluctuate. Because energy varies, microstates are no longer equally probable. A state's likelihood now depends on the reservoir's temperature. Each state is weighted by the Boltzmann factor, e to the negative beta EI, where beta is the inverse of temperature times Boltzmann's constant. The sum of these weighted probabilities across all possible states is the canonical partition function, Z. Z acts as the bridge to macroscopic thermodynamics through the Helmholtz free energy F, allowing us to calculate pressure, determine the system's entropy, and find the chemical potential. Although energy fluctuations add complexity, the resulting partition functions are often easier to compute for non-interacting systems than the microcanonical count. The grand canonical ensemble models open systems, where both energy and particles can transfer across the boundary. Here, volume and temperature are fixed alongside the chemical potential, mu. Both the total number of particles and the internal energy fluctuate. The statistical weight now accounts for both variables, with higher energy and higher particle counts becoming exponentially less probable. The grand canonical partition function is a nested sum over all possible particle numbers and their corresponding energy states. This framework yields the grand potential, which is directly proportional to the system's pressure and volume. These three ensembles use different boundary rules and allow different fluctuations. However, in macroscopic systems, these fluctuations become negligible, leading to a single thermodynamic result. If the canonical and grand canonical ensembles permit continuous fluctuations, it is not immediately obvious why they yield the same results as the fixed microcanonical ensemble. The resolution lies in the thermodynamic limit, where the particle number n and volume v approach infinity, while the density stays constant. As the system size increases, the magnitude of the fluctuations relative to the average values decreases. For small systems, the energy probability distribution is broad, The relative standard deviation scales as 1 over the square root of n. As n approaches 10 to the 23rd, the distribution violently narrows into an extremely sharp spike. The relative fluctuation becomes effectively 0. In this limit, the average values in the fluctuating ensembles become indistinguishable from the fixed values in the microcanonical ensemble. We demonstrate this equivalence mathematically by examining the integral inside the canonical partition function. The integral has two competing terms. The density of states, omega, increases rapidly with energy, while the Boltzmann factor decays exponentially. Their product creates a single narrow peak at the thermodynamic average energy, E star. At large n, this peak dominates the integral, the saddle point approximation. Because only this peak contributes significantly to the result, the canonical Helmholtz free energy mathematically reduces to the microcanonical entropy. This equivalence holds for systems with short-range interactions. It can fail in systems with long-range forces like gravity, or during first-order phase transitions where states coexist. Statistical mechanics allows us to choose whichever ensemble is most mathematically convenient for a given set of boundaries, knowing that at macroscopic scales, they all converge into the same thermodynamic laws.